Hello, I am Marcelo Miranda. I'm a lecturer in the School of Chemistry of the University of Leeds. I'm here today to talk about endothermic reactions. That's reactions that absorb heat as they go. Most endothermic reactions, they won't go by themselves. They need to be powered, much like a fridge needs powering to get cool inside. But there are some examples of chemical reactions that are endothermic and are spontaneous. They absorb heat all by themselves, cooling the environment around them. Let me give you an example. Okay, so here we are. What you have here is a little bit of ammonium nitrate, some water, and a thermometer. The thermometer is measuring the temperature here where we have the ammonium nitrate. What's going to happen is that as I drop the water onto the ammonium nitrate, the water and the ammonium nitrate are going to react. The temperature is going to go down. The temperature, please keep your eyes on it, is the bottom number here at the thermometer. I'm going to drop the water. And I'm going to mix. Very soon, the temperature should start going down. Please bear with me. This is a thermometer that I got off of my kid's bedroom. It doesn't go too quickly, but eventually the temperature will drop. I'll keep stirring, mixing the ammonium nitrate in the water, and the temperature will go down. That's the bottom number on the thermometer. There is the temperature going down. An endothermic reaction that doesn't need me to power it or to do anything to it. It just happens by itself. All right, so if you want to understand how this thing happens, how this chemical reaction can pump heat out of the environment, cooling things down, there are two clues that you need to have. The first clue has to do with how energy is distributed among a set of identical molecules. The second clue is how that energy is distributed when you have two different types of molecules, which may be the reagent molecules and the product molecules. So the first clue that you need to have is about how energy gets distributed across a bunch of molecules. I've put here an arrow showing the energy going up and three amounts of energy the molecules might absorb. These molecules might absorb little energy, they would have low energy, or they would have intermediate energy, or they would have high energy. The second thing that you need to know is that when molecules pick up energy, they tend to pick up less. So you're going to find more molecules with less energy. Actually, if you look at zero temperature, absolutely zero Kelvin of temperature, and you have this number of molecules, you're going to find them, all of them, in the very lowest energy level. If you go to infinite temperature, then the molecules are spread all over the energy levels. Please note that they don't go all to the upper energy level, they get evenly spread. And that's an intermediate situation, the thing that I said before. Well, the molecules pile up in the low energy level, there's going to be a few in the intermediate energy level, and fewer still on the top energy levels. That's what happened at an intermediate temperature that is neither zero nor infinity. It's pretty much as if you had a bookshelf and you want to put books on it, and the shelves are harder and harder to reach. Chances are you're going to put your first few books on the bookshelf, well, if you have not too many books and the shelf is very easy to reach, you can put them all on the lower shelves. But if you have, well, more books to put, that shelf is getting full, you're going to start putting on the next shelf that is hard to read, and maybe you're finding that's getting full as well. You might put your last book on the top shelf. That's pretty much how energy gets distributed across a bunch of molecules at a given temperature. There's a formula to calculate this in the case of molecules at a certain temperature. It's called the Boltzmann distribution. Okay, that's the end of this part one. Now I'm going to go to part two. So now we come to the second of those two clues that you need to have to understand how come endothermic reactions can be spontaneous. We are back to that energy diagram showing energy levels, in this case assuming reagents for the reaction, things that you have at the start, and at a certain temperature, let's assume that things are like this. you have initially a lot of reagent molecules on the very lowest energy level, and as you go up in energy, you have fewer and fewer of the reagent molecules at those energy levels. The populations of molecules on energy levels go down as you go up in energy. Now let's look at the situation that happens for most endothermic reactions. Well, these levels that I've put here now, they are the energy levels for the product molecules, and you see that they are always a little bit above the reagent energy levels. Well, if that's the situation, what's going to happen is that when the situation comes to equilibrium, you're going to have more reagent molecules than you have product molecules. If I put the difference a little bit bigger, you hardly would have any product molecules at all. In any case, this reaction is not spontaneous in the sense that it's not going to transform lots of reagent molecules into product molecules. That's only going to happen to a small extent, if at all. That's the situation for most endothermic reactions, those that you need to power, to drive for them to take place, much as you need to power your fridge to get it cooled down in your kitchen. Now let's look at the situation that corresponds to spontaneous endothermic reactions, like the ones that we have seen in our demonstration earlier on. Okay. All right, so now we are going to look at the situation that, while still corresponding to endothermic reactions, is different from what we looked at before. We're now going to look at something that might make an endothermic reaction spontaneous. To start with, we still have here the energy levels for the reagent molecules, those that are there at the beginning of the reaction, and at the beginning of the reaction, at any given temperature, we're going to have more molecules in the lowest energy state and fewer as you go up in energy. So these are the energy levels for the reagents. Now let's say that the energy levels for the products are like this, these squares that I put here now. They are still above certainly the lowest energy level of the reagents, but they are packed very closely. And now let's look at a certain temperature, how the molecules get distributed among these energy levels. Well, as is always the case, the population goes down as you go up in energy level. But please notice that now, because there are so many product energy levels that are close to each other, the populations, the number of molecules in each of them, they go down only very slowly. And when you add up these numbers of molecules that are actually populating product states, well, you can end up in a situation like this. In this figure here, we have 61% of my molecules in the shape of products, 39% in the shape of reagents. If that's your situation, well, heat is going to have to be used to move energies from here to those levels up, but in the end, because of the way energy is distributed, you're going to have more product molecules than you have reagent molecules. That's an endothermic reaction that is spontaneous. So now you know how come some endothermic reactions can be spontaneous. The key is in the energy distribution among the molecules of reagents and products, which depends on how high the energy levels of these molecules are. If the product molecules have energy levels that are above the lowest state of the reagent molecules, but not too much above, and lots of energy levels around there, the reaction may well be spontaneous. That's the end of this podcast today. Thank you very much for watching.